All right, let's take a look at this problem. This is a really kind of nice but fairly straightforward angular momentum problem. And we have a collision, not a surprise, right? You remember from linear momentum that we usually pulled out momentum analysis when we had either a collision or explosion, something that happened over a very short time and that involved fairly complex internal forces. So we felt like we couldn't get a handle on it using force analysis or energy analysis. So we would use momentum analysis. So this is really the same. The motivation is the same. In this problem, we have a solid cylinder that's initially at rest. So that's the big circle that you're seeing is a cross section of a solid cylinder. The axis of rotation is at the center of the cylinder and it is fixed axis. So the cylinder is held in place by the center of the mass of the cylinder is held in place due to a fixed axis. Okay, so the cylinder, we're not talking about something rolling here. And what we do is we fire a ball of clay at the cylinder, and the cylinder is initially at rest. The ball of clay gets fired at the cylinder, and then this is fairly intuitive to see that what would happen then is that you'd have the cylinder would then have angular velocity direction into the page there caused by that collision. So the impact point of that collision is going to be like right here. That's your impact. That's important, right? That's your impact point. Okay. We're told there, part of what we're told in this problem is that the impact point happens at 4/5 r. So that's why I've drawn it out in the diagram like that. All right. So we're asked to determine the angular speed of the system after the clay hits, and we're told to assume a completely inelastic collision. You remember what that means, right? That means that the clay sticks onto the cylinder there. It doesn't bounce off. It's completely inelastic. So that means the two objects stick together and move together after that point. So the first question you want to ask yourself here is can we, when we're applying conservation of momentum, like can we say that the change in angular momentum is equal to 0 for this case? How can we make the justification for that? And I would say you always need to pause. If you're using conservation of momentum, you always need to pause at this point and ask yourself this question before just reflexively using it. And so first of all, if I'm going to be using this, I need to define my system and I'll say, okay, the system is going to be the ball of clay plus the cylinder. And I have to define it that way such that all the messy forces that happen at the collision, all those messy forces that we can't get at, those are all internal forces then, if I define my system as being the system of those two bodies. Great. So I have my system defined that way that takes care of those messy collision forces. I mean, the clay is going to deform, there's going to be all kinds of stuff. Energy is totally going to be lost here. Anytime you have a completely inelastic collision, there's either some kind of like a mechanical reason for it or deformation that happens. A nice example I like to give of completely inelastic collisions is an example of a plane landing on an aircraft carrier. I think that's a neat example. And you know that like the reason that happens is because the cable catches on to the plane, right? So there are all kinds of messy forces at work there, and energy is completely not conserved there, mechanical energy. Obviously not. You have this plane that comes roaring down, and then the plane is at rest with respect to the aircraft carrier, right? So a lot of what happens there is some kind of mechanical situation. In that case, it's a cable. But whenever you have a completely inelastic collision, two objects that stick together, there is some kind of reason that they stick together. And whatever mechanism is causing that is a mechanism that typically dissipates mechanical energy. Okay, I'll leave that alone. So that's our system. The next question is, can we say that there are no external forces? So we want to stop and say, what are my external forces? So if there are any external forces to this system here, net external forces, right? I should say net, then we know we can't use this conservation of momentum, or we can't say change in momentum is 0, because we know that remember, this is the original communication of Newton's second law, sum of forces is equal to the change in, oh, I'm sorry, so this will be torques right now. sum of torques is equal to the change in angular momentum over time. So that's all that is really is the angular analog to second law, right? Okay. So this is me saying like the net external forces are what are going to cause external torques, right? So we need to look at those. Okay, so if I look at the ball of clay itself, it could be argued that, well, there is gravitational force on this ball of clay. So what we say is we say that, well, this is all happening fast enough. And let's say that this V prime speed, I'm going to assume that's the speed this ball of clay has right before the impact point. So this all happens in a very, very, very small amount of time. It's going really fast. I don't have to worry about the gravitational force or the weight on the ball of clay. I'm going to have to make that assumption in order to use this. And again, remember, if I don't use conservation of momentum here, I don't have any tools because I don't have the information that I need about those internal forces. So we can say, yeah, we can neglect gravitational force on the ball of clay. So we'll do that. We'll assume V prime is really big and the time interval is really short. And then that'll allow us to use this tool. If I look at the cylinder itself, I don't have any net external forces on it. Yes, the cylinder has weight. It also is being supported by the normal force at the axis of rotation. We're told that the axis is fixed. This is a fixed axis situation, so I don't have to worry about any external forces there. So that running through that logic in my mind tells me that yes, I can go ahead and use this. So what this means is that I need to look at the angular momentum before and after the collision. So you set these problems up just like you set them up for linear momentum. So if you remember, you looked at the instant before the collision and the instant after the collision. You want to close that time window down nice and narrow for using this tool. And in this particular problem, we're not looking at any other process before or process after. We're really only looking at the collision. It's a very short analysis window. So if I look at my initial angular momentum here, initially the angular momentum is all in the ball of clay, right? Because initially the cylinder is not moving at all. We don't have any angular momentum. There's no rotation, nothing going on in the cylinder. So I know that initially everything is in the ball of clay. So that ball of clay is a particle, yeah? So I can think of the ball of clay, I'm going to consider here R cross P. If you look at the equation for angular momentum, when you're looking at angular momentum of a particle, we're just taking the cross product of R. We can talk about what R is in just a second. And P is the linear momentum. So this is the initial linear momentum of the particle, and then cross that with R. Now, R is going to be the location of the particle right before impact. So that R is going to be, I'll draw it on the physical diagram. This is what I mean here. R little m. The axis of rotation of the system, the axis of rotation of the system is going to be the axis of rotation of the cylinder. Because remember, right, we're looking at this, we have to look at the same axis of rotation before and after when we apply a conservation of angular momentum. And that axis of rotation is fixed for this cylinder. All right, so what that gives me for this case, that radius there. Now, I want you to think about it. We're going to be looking at this cross product, right? So maybe it'll help here if I also draw in the vector for the linear momentum of the ball. So if I'm looking at the linear momentum of the ball, I'll draw that in here. Here is the initial linear momentum of the clay ball. So now I'm taking a cross product between these two vectors, vector r sub m and then p, right? So look at those two. Think about the fact that you're taking a cross product between those two. And in a cross product or vector product, really what happens is, a way to think about this physically is that all of the parallel components between the two vectors get filtered out. And all you're left with at the end of a cross or vector product is a product of the of the components of the two vectors that are normal to one another. So really, I'm only left with the product of the two vectors that are normal. And you can visualize that in different ways. In this particular problem, I find it is easiest to envision, let's see, I'm going to use a different color for this, that as if I draw in this vector right here, I can call this r sub m perpendicular or something, right? So this green vector represents the component of the vector r that is normal to the vector p, right? And what's super cool about this is that component of rm, that rm perpendicular, it's equal to 4/5 r. I have that right there in my diagram. So when I'm figuring out what this is actually just going to give me 4/5 r times, and then linear momentum is just going to be mv prime here. And that's all into the page, right-hand rule. So remember that this is r crossing into p, right? Not p crossing into r. So vector product is not commutative. The order matters. So you can get the into the page direction for that cross product. Okay. So you might need to spend a little more time with that, or maybe show that to yourself in a couple different ways. I'm going to leave it alone there. The final momentum, this is post-collision, okay, after the collision. Now what's going on is these two things are stuck together and the cylinder is rotating. So a way I can think about this is now the I value for the clay mass times omega final, that would be vector, plus the I value for the cylinder times omega final. These omega finals are going to be the same. Remember that the ball of clay sticks to the cylinder. We're told it's a completely inelastic collision. So this here, final angular momentum, I can simplify this a little bit here. Omega final mr squared, that's just the I value for a particle, plus 1/2 big M r squared, that's for the cylinder. And this is vector, right? That's into the page. Great. So none of the directions change or anything like that. We have these things moving together. So both my initial, of course, my initial and final angular momenta have to have the same direction. It's if it's a conserved quantity. So then I can set those equal to each other, which is kind of cool. So then all I will do at this point is just say, if I can say then that change in angular momentum is equal to 0, then that helps me say that the initial is equal to the final angular momentum. They're the same direction, so we'll just go ahead and set their magnitudes equal then. So 4/5 r mv prime is equal to omega final r squared times m plus 1/2 big M. Okay, so that's the equation that I'll use from there, and that will allow me to solve for omega final, which is what I'm being asked for in this problem, right? The angular speed of the system after the collision. And what we should get then for that is 4mv prime over 5r m plus 1/2 big M.